Different ways we're going to solve nonlinear systems is algebraic methods. That would be elimination, substitution, that style of solving systems. And then we're going to talk about using graphing those results and also sometimes to find those. There are limitations to graphing because you can't give exact answers sometimes. Like if the answer is the square root of 10, if you look at the graph on your calculator, you're not going to know that it's the square root of 10. You'll know it's 3 point something, but you won't know, unless you're familiar with that number a lot. You won't necessarily recognize it as the square root of 10. So there are limitations to graphing. The same limitations that occurred when we solved systems with graphing back in Algebra 1, when you would graph and it wouldn't land at a nice lattice point or where a place on the grid, you had to estimate where it was at. Same thing happens when we're doing nonlinear systems. So let's look at this first one and talk about the different methods that we could use to solve this linear system or nonlinear system. We have the first equation is a linear equation because it doesn't have an exponent on either of the variables, right? So we could get it in slope-intercept form. That tells us it's a linear equation. But the second one is what kind of equation? Quadratic, because it's got an x squared. So we know that this thing, if we were to graph this, we're going to do that later, we would have a parabola and a line, and we're looking for where they intersect is what we're looking for out of that. So there's a couple of different ways to do this one. I like elimination a lot of times, especially when it's already set up like this. But substitution works wonderfully as well for this one. But if I were going to do elimination with this one, notice that I have 3x minus y, and the second equation has a 2x squared minus y. So I've got some similarity there. I don't have opposites, so I need to get opposites out of that. So I'm going to take the first equation and just multiply it by -1. And that'll give me -3x plus y is equal to +2. And the second equation, I'm just going to copy it down. 2x squared minus y equals 0. And then when I take that system and I add those two together, what happens to the y's? They cancel each other. They eliminate one another. And I get 2x squared and -3x. Are those like terms? No, so I can't really put them together, but I can write this, which gives me a quadratic equation to solve at the end. So not quite as easy as doing elimination with linear systems because we don't have that one-step equation to solve here at the end, but we do have a quadratic, and we know how to solve quadratics. So tell me what to do. Yeah, get the 2 to the other side to get it equal to 0. 2x squared minus 3x minus 2 equals 0. And then what are my options? Factoring with the x method. What other options? Quadratic formula is always an option there. Remember, factoring doesn't always work. It does on this one, but factoring is not always going to be an option. Quadratic formula is always an option. You are welcome to do quadratic formula every time. I don't care. I'm going to use factoring on this one because it works real nice. But quadratic formula will work each time on a quadratic equation. This one, we can do factoring. So we always like factoring. It's fun. -4 and 1. 2x squared minus 4x plus 1x minus 2. Group 2x, x minus 2 plus 1, x minus 2. So my factors are 2x plus 1 and x minus 2. So I get x values of -1/2 and 2. I get 2 x values out of that, which means I should find how many y values? 2 of them. How do I find those y values? Plug those in. Where? One of the equations. It doesn't matter which one. Pick the one you feel like is the easiest. I would go for the linear one because it is much easier to do to solve a linear equation. So I'm going to take 3 times negative 1/2 minus y is equal to 2. Solve that. So negative 3 over 2 minus y equals 2. Add 3 over 2, negative y is equal to 7 over 2. And it is a negative 2. Thank you. That's going to make a difference. Thank you for catching that mistake. So the original was a negative 2 on that side. So now let's do that correctly. And so add 3 over 2 to negative 2. So that'd be 1/2. Negative 1/2. And then so y is equal to 1/2 or positive 1/2. So we get an ordered pair when x is negative 1/2, y is positive 1/2. So there's one of our solutions. Let's do the same work, but plugging 2 in for x. 2 times 2 minus y equals negative 2. And so 6 minus y equals negative 2. Negative y is equal to negative 8. Y is equal to 8. So the other ordered pair we have is 2, 8. So we should see those two equations, the graphs of them crossing at these two places. Okay, so we're actually gonna do that with graphs now, and verify that this is what's happening. That we found those algebraically. Let's show how to find those graphically. Well, the limitation of your graphing calculator is that in order to graph something, what do you have to have by itself? Y. So graphically, you know, 3x minus y equals negative 2. If you get y by itself, it's going to be y equals 3x plus 2, right? Subtract 3x, then divide by negative 1. You get 3x plus 2. And then 2x squared minus y equals 0. Get y by itself, you're going to have y equals 2x squared for the parabola part. And we're going to graph each of those on the graphic calculator and see where they cross. So y equals 3x plus 2. And then on the second one, 2x squared. Hit graph. So there's our line, and there is our parabola, and we see them crossing. I think that they're crossing at negative 1/2. 1/2 is that, so I could hit trace and type in negative 1/2. And I verify there. I see the y value is 0.5 as well, so that verifies there. And also at 2, 8. So if I hit trace 2, hit enter, I get out there 2, 8. If I swap over to that, the red one, and hit 2, also get 8 out of that. So we're seeing those intersections there. Now, here's the great thing about your graphing calculator. It will actually find those intersections for you. So if you hit second trace in the calculate menu, number 5 is an intersect tool. So I'm going to select that. And it's going to ask you which one's the first curve. And notice how it's got Y1 selected. That's the one I want to look at. And then Y2 is the second curve. And then it wants to say, which intersection do you want? The guess is important here because you put that closest to the one you're trying to find. So I'm already close to the one that I think is at 2, 8. I think that's it. So I'm going to hit enter. And it shows me the intersection is at 2, 8. Out of that, I go through the same process. Second trace, select intersect. The first curve, it shows me Y1. I'm going to go ahead and move my cursor down here close to where that intersection is. And then this one, second curve is the Y2. Those are the only two I have in. The reason it asks you that is because your calculator will do up to 10 graphs at the same time. So you might have multiple ones there. It's a redundant part of the programming there. The guess, it asks us to guess where that is. You want it closest to the intersection that you're trying to find. If you put it kind of closer to the one up there at 2, 8, it's going to find that one again. So wherever your guess is closest to, that's the intersection it's going to find. So I'm thinking that's pretty close. And there is my negative 1/2, positive 1/2 out of there. So you use the intersection tool with your graphing calculator. This one's nice because they're the numbers we found algebraically are, terminating decimals or, lattice points with integers as the x and y values. So it makes it easy to get there, but that's not always going to be the case. That. Okay, but we can still use that intersection tool to help us verify results. That. Algebraically is always going to outrank graphically just because you can get exact answers. Graphically, you're going to be limited to, the decimal approximation there on that. So let's look at another one. X squared plus y squared equals 13. Does anybody know what that's the equation of from maybe geometry class? Think shapes. Circle. It's the equation of a circle. X squared plus y squared equals 13 is the equation of a circle centered at 0, 0 with a radius of the square root of 13 is what that is. You may not remember that from geometry, but that's what that is. Not that it's really necessary to know that. I'm just trying to give you some general knowledge. And then this one you probably haven't seen before. This one is a hyperbola equation. And so this is what we've got going on. We've got a circle and a hyperbola. A hyperbola looks kind of like this. It's like a parabola type shape, but two of them mirroring each other back to back there. So it kind of almost makes a baseball shape. Yeah. So out of that, when you combine those two as a system. So we could have 4 solutions to this one. That doesn't mean we will have 4 solutions, but we could out of that. Notice, we got x squared and y squared, so there's 2 x's and 2 y's that go with that, so that's total 4. That kind of can give you an idea. But if you were to just pick up the hyperbola and slide it down a little bit to where this one is, maybe they're wider apart, it's possible that you only have 2 solutions out of that. It's also possible that you don't have any, because that's a system of equations, so that stuff can happen. So we're going to algebraically find what the solutions are, and then we're going to talk about how to do that graphically as well. All right, so we know, just some general knowledge, that's what could be happening here. We don't know for sure that that's what's happening. We'll verify that when we find these answers out of that. So again, you can use substitution. You could use elimination. I think elimination would be a great one for this one, because what do we see? We got y squared and negative y squared. We got opposites there. So if we add these 2 equations together, the y squareds are going to cancel out. Now we get 2x squared is equal to 20. And that is an easier problem to solve. How do we solve that? Divide by 2 would be a good start. So to get x by itself, we take the square root. But if we introduce a square root to a problem, it has to have plus or minus on the front of it. So we get 2 x values. We get positive square root of 10 and negative square root of 10. How do we get the y values that go with that? Plug them into one of the equations. I'm going to go to the first one. It technically does not matter which one. I'm going to go to the first one because it's only got positive signs in it. So that makes it seem easier, because I don't have to deal with putting in an extra negative. So I'm going to plug in the square root of 10 for x. And then when I square the square root of 10, I get 10. I subtract 10. Y squared is equal to 3. And then I take the square root. And I introduced a square root, so I got to have plus or minus. So when x is the square root of 10, I actually get 2 y values that go with that. I get a y value of positive square root of 3. And then I get square root of 10 negative square root of 3. Then I'm going to do the same work plugging in negative square root of 10 for x. That's just going to be 10. It looks like it's going to be the same numbers. So I have the ordered pairs negative square root of 10, positive square root of 3, negative square root of 10, negative square root of 3. So here we have 4 solutions to that system of equations. All 4 of those ordered pairs. None of which are integers or even rational. They're all irrational numbers. So that would have been one that would have been very difficult to find the exact answers for if we do that graphically. Graphically, this is a little bit more difficult because we have squareds on our y's. Okay, and your graphing calculator needs what by itself in order to graph something? Y. Okay, so let's look at doing that graphically. Bless you. Graphically, we've got to get y by itself. So x squared plus y squared equals 13. If we're working to get y by itself, I've got to do what next to get y? I got to take the square root of both sides. And if I do that, I got to put plus or minus on there. So I've got plus or minus the square root of negative x squared plus 13. So when I graph that, I've got to graph a positive square root of negative x squared plus 13. And then on another equation, graph the negative square root of negative x squared plus 13 to get it to draw the circle, because it can't draw it. There's no plus or minus button there that you can use. Okay, so let's do that. So the first 2 equations are going to be my circle. I'm going to have the square root of negative x squared plus 13. And on the second one, I'm going to have negative square root of x squared plus 13. I'm going to show you what that graph looks like. Whoops. I'll type in differently there. That's not the negative x on the inside. Yeah, I did put that in there. Second insert negative. There we go. All right, now that doesn't look too much like a circle. I'm going to hit zoom 5 to make it a square picture. Now it looks a little bit more like a circle. Those actually will connect there. The resolution gets a little too high there for it to draw the connection between those two. But you can see it makes a circle. I changed that to zoom square just so you can see the circle. Your calculator screen natural orientation is not square. It's 10 by 10, but it's not perfectly pixelated for nice picture there. So we see a circle. Let's get the other equations. So we got x squared minus y squared equals 7. Same kind of work is happening here. To get y by itself, we subtract x squared, negative x squared plus 7. Then we got to divide by negative 1. X squared minus 7. And then we take the square root, so plus or minus the square root of x squared minus 7. And then on my calculator, y3 and y4 are going to be those parts. So we got the positive square root of x squared minus 7, and then the negative square root of x squared minus 7. Graph on those. There we have the parabola. I had mine oriented the other way horizontally. This one happens to be a vertical one there. But we see, again, these do connect. The resolution gets a little too tight for it to draw that going in there. But that does happen there. And we see how many places is it crossing? 4 places. Right here, right here, right here, right here. We could use the intersect function on the calculator to find each of those places. We've got to keep in mind which one of those is what equation when we do that. So this is where knowing what curve you're using. Okay, so the black one is y3, the blue one is y1. Okay, so when I do that intersect, second trace, intersect, I've got the first curve is y1. The second curve, I'm going to move to y3. And then I'm going to move my cursor. I'm on y3. Let's see, over here. There we go. And then my guess is going to be, the closest intersection to that point. Negative 3.162278. That's the square root of, that's a negative square root of 10 for the x value. And then 1.73 is the square root of 3 of that, which is one of the ordered pairs that we found there. Negative square root of 10, square root of 3. And then we could do the same thing. Second trace, intersect. First curve, we're on y1. Second curve, let's go to y3. And then my guess is going to be way on the other side here. Right there. And the intersection again, positive square root of 10. That's positive square root of 3. We could do the same things for the bottom ones. Again, not the best, way of getting all our answers. Algebraically is going to be, better, but we can see that it, what's going on with it graphically to get those solutions out of that. All right, so you could do the intersect for the other two if you wanted to. All right, let's look at one more. X squared minus y squared equals 4, and y equals x squared. They have a hyperbola and a parabola. What this one is. What method would be good to solve this in? Okay, that would be one way of doing that. So if I subtract x squared to get it over here, that would give me negative x squared plus y is equal to 0. And then the top one didn't change, x squared minus y squared equals 4. And yes, you do elimination from there, works wonderfully, cancels out. Negative y squared plus y equals 4. And so we got a quadratic to solve to get some answers. We're getting y first this time, but it doesn't really matter. Works the same. So it'd be negative y squared plus y minus 4 equals 0. I'm going to go ahead and flip all the signs just so it makes it easier to do quadratic formula with, so I don't have to deal with the extra negatives in there with the A. And so I'm going to do quadratic formula on this one because I don't know anything that multiplies to be 4 and adds to be negative 1. So that's why I'm going that route. Positive 1 plus or minus b squared minus 4ac. So negative 1 squared minus 4 times 1 times 4 over 2 times 1. So that's 1 plus or minus the square root of 1 minus 16, which is negative 15 over 2. What does this tell us? It's imaginary numbers. That's complex solutions. Do complex solutions show up on graphs? No. This tells us that it's complex, which means there's no real solutions. And we're done. Because that's complex, they don't show up. If we were to graph these two, get y by itself on the hyperbola and graph it, we would see that they don't intersect. They don't cross each other. How of that? So you could do that graphically if you wanted to. Okay. So anytime you get complex solutions in there, you know that that's not an answer. You just throw that out. Okay. There's not much else to it. This is pretty straightforward. Not quite as easy as what we've been doing the last few days. So we gotta beef it up a little bit, make it a little tough. It's college, so. But nonlinear systems, probably more in real world situations, probably more likely because not everything's a straight line, right? So curved lines are more prevalent in the world. So suggested problems. This is quite a random list here. So 5 through 12, 15 through 18. Okay, here we go. 21, 23, 26, 27, 28, 33, 34, 35, 36, 39, 40, 41, and 42. So don't normally do that, but that's some of those I could have consolidated a little bit, but just get to go and make a list. All right. So those are your practice problems for this section.